Monday will be the second one in the book, characterizing an unknown something or other.
Okay. We posted those labs as well.
Yep. All right, let's go ahead and get started. You know, this, of course, always begins with a little bit of review. We've been talking about matter, we've been talking about atoms and stuff like that. Let's start off with the nucleus here. Again, we know we have protons and neutrons in the nucleus. Protons are positively charged, neutrons are neutral, and electrons are negatively charged, and they live in the region surrounding the nucleus. Again, protons are positive, electrons are negative, and neutrons are neutral. If you have the same number of protons and electrons in an atom, then it will be a neutral atom. We'll see today that you can have more or fewer electrons and protons, and that will make it what we call an ion. Subatomic particles. You know, we talk about protons and the nucleus and all of this stuff. Turns out that there's a whole lot more to it than just that. There are lots and lots and lots of subatomic particles as well. The major particles that we're going to address in this chapter are going to be alpha particles, beta, and a little bit about gamma particles, because gammas are a little bit strange. This is a very classic image. Back in 1896, you couldn't just go out and buy photographic plates. You had to make them, and it was a real pain. And these guys, French, were working on phosphorescence, I believe. And so they used photographic plates. And they had them sitting there in a nice dark place, just like you're supposed to. And somebody went and put a bottle of uranium salt on top of it. Well, they went ahead and did their experiment. They had no idea. And when they developed it, they saw that where the uranium was, there were these big, ugly splotches, and somebody ruined their plates. Now, they were probably very upset by that, but this is the phenomena of radioactivity. Radioactivity, on the very simple level, starts in the nucleus. We have two types of real nuclear particles that are going to come out. One is an alpha. An alpha particle is literally a helium nucleus. It's 2 protons and 2 neutrons. It weighs a lot, it's heavy, slow, can be very, very dangerous. The other thing that we'll talk about is a beta particle. Beta particles, a neutron, like we said, is neutral, but it can actually decompose. And when it does, it makes a proton, positive, and a beta particle, which is really an electron, and it ejects the electron from the nucleus. So that is the beta particle as it flies out. These guys all have different energies. Alpha particles, like I said, are big and slow. A single piece of paper will typically stop an alpha particle. Betas have much more energy. They could go through like a centimeter of lead. Gamma particles can be very, very high energy. They can go through like 10 centimeters of lead. It can be very, very dangerous. Actually, alpha particles are perhaps the most dangerous to people. One of the deadliest elements known is plutonium. Now, plutonium's used in bombs. It's everywhere, frankly. But the real danger isn't so much the bomb blowing up, although that's not fun. But the real danger from plutonium is that if there's any that's left over, it's dispersed very, very finely. About 1 microgram, that's 1/1,000,000 of a gram, is enough to kill you. Now, you might say, gee, plutonium turns out to be an alpha emitter. And I said, you know, they're real slow and stuff like that. Problem is that you can inhale this. So little tiny bits get in you. And they just sit there in your lung, if they don't go anywhere. And they slowly irradiate you from the inside out. The alpha particles travel right up to your cell, and they mess with the nuclei, and pretty soon you're dead. Polonium is actually even much more dangerous than plutonium. But this is a Geiger counter. I actually went and got one. Geiger counter, you have a tube here. This is the tube. And the thing places a voltage on the tube. The thing is full of a gas here. And it's at high vacuum. And every time a radioactive particle comes flying in here, it leaves a trail of ionization. When it does that, the high voltage, like a little spark, lightning or whatever, arcs across, and you get the traditional click. I just happen to have a little bottle of uranium nitrate, which I always use for this. And you heard the little tiny click. Just sitting here in the room, every now and then you'll get a click, typically as a gamma ray comes from outer space or something. But lots of little stuff coming out of here. Now this is what's called depleted uranium. Depleted uranium. So this isn't the good stuff. Uranium is a very interesting metal. It's hard, and it's very, very dense. Okay? When they make bombs, they use lots and lots of uranium-238, common isotope, and that's all left over, and that's what that is. They take out the 235, which is the stuff that floats up. The depleted uranium, they go ahead and refine it to the metal, and then they use it to make armor-piercing shells. Perhaps you guys remember there was a war in Iraq some time ago, and these waves of tanks would come, and these little airplanes were there shooting these 2 centimeter shells at them. And that was depleted uranium. It's all over that desert now. Uranium actually emits alpha particles until it gets down to thorium, and then it does beta and whatever. But that's just interesting, I think. All right. When you have something that does this, that decomposes, we say that this guy is radioactive. Now, radioactivity has been known for a very, very long time, again, since 1896 or so. It's a very interesting use that Rutherford devised that allowed him to actually take a measurement of a nucleus, exactly how large a nucleus was. This is amazing, an amazing experiment. He took an alpha particle source, so something like a little bottle of uranium, had a pinhole, and then took very, very thin gold sheet. Remember I said gold was very malleable? You could pound it down so it just basically just atoms thick. 1 or 2 atoms, actually. Well, he put this little gold foil there, let the alpha particles run through here. Most of the space in an element, in an atom, is empty space. And his reasoning was that as these alpha particles go, and they're coming in a moment, there they come. When they get close to the positive nucleus, they're going to be repelled. And as they're repelled, they bounce off, and they show up on the sides here. Now, he can tell where they go by looking at the little fluorescent dots that show up. based on that, based on this experiment, he was actually able to measure the size of a nucleus, and it's about 10 to the minus 15 meters. That's a wee tiny thing. A beautiful experiment. Again, about 10 to the minus 15 meters for the nucleus. The electron cloud is huge relative to that. All right, any question on the concepts here? We were talking about elements. We talked a lot about it. We know that they're arranged in the periodic table. We know that they all have a chemical symbol. This is our traditional periodic table. The one you get on exams will look very much like this one. Periods up and down, and groups going across. We tend to talk about groups 1 through 8, even though there are 18 going across. Now, if you look at your periodic table here, you'll see two types of nomenclature, 1 to 18 and 1 to 8. Today we'll realize why 1 to 8 is so popular, because it helps us understand bonding. Now, we talked about the periodic table and the fact that it's arranged by atomic number. Atomic number, remember, is the number of protons in the nucleus. The one thing that distinguishes what an element is the number of protons in its nucleus. We all remember that, right? Okay, remember this tutorial? I hope you've done it and gotten your credit for it. What if I gave you this as a tutorial question? You are given that your element is oxygen. We are given a mass number. Remember, the mass number is the number of protons and neutrons. And we're given a charge. Charge is 0. All right, oxygen is here. First thing we do is we look and say, okay, atomic number is 8. That means we have how many protons? Well, we have 8. Now, if the mass number is 16 and 8 of those are protons, the other 8 must be neutrons. Finally, if our element is neutral, that means we must have the same number of positives and negatives. We have 8 positives, we must have 8 negatives. We've all done that. We can do this. This is the sort of thing you should be able to do on the exam. Any questions on it? Well, what if I had changed this problem just a little bit? What, instead of having mass number 16, here's what we did. What if I had put in mass number 18? Well, you would do this problem the same way, wouldn't you? You'd say, all right, if our mass number is 18, and 8 of those are protons, we must have 10 neutrons, not 8. This is still oxygen, isn't it? Because it has 8 protons. This is the concept of isotopes. Let's look at carbon as an example. Carbon has atomic number of 6. Typically, carbon has 6 protons and 6 neutrons. This is what the nucleus would look like with 6 protons and 6 neutrons. We'll see today that the electrons and carbon are actually arranged in 2 shells, an inner shell and an outer, but we'll get to those in a minute. What if we took this nucleus? Oh, this is the atomic symbol we would write. Remember the atomic symbol. Mass number up top, atomic number on the bottom. What if we took this nucleus and we added one more neutron? Well, it still only has 6 protons, but now its mass number is 13. With carbon, we can do this again. And now we have 6 protons, and we have 8 neutrons. This is carbon 14. This is what's referred to as isotopes. Isotopes have different masses, but they have the same number of protons. Carbon-12 is the most common. This is the one that we see all the time. You've probably heard of carbon-14. Carbon-14 is used for dating, isn't it? Because carbon-14 is radioactive, and it decomposes. And as it does it at a very steady rate. And by measuring how much carbon-14 is left, you can tell when a living thing stopped living. So it's very, very good as far as doing that. Carbon-14 is present just as a trace. We talk about the 3 isotopes. We tend to just leave out the 6, and we say this is carbon-12, 13, and 14. Now, when you're talking about carbon as we see it, charcoal, whatever, carbon, plain old carbon, we're going to have different abundance. In our universe right here, right now, 98.89% of carbon is going to be C12. So that's almost all of it. You're going to have a little over 1% of carbon that's C13. And if you get to organic chemistry, you'll see that carbon-13 is a very, very important isotope for organic chemistry. Trace amount is going to be the C14, and that's the radioactive one. If you note in the periodic table, and you look at the average atomic mass of carbon, it's not 12, but it's got to be adjusted for the fact that we have mostly 12, a little bit of 13, and just a trace of 14. We do the calculation like this. This is the fraction. So 98% is 0.98. 12 is the mass. And we're adding to that our 1%, 13. And carbon-14 is so small we don't even bother. If you do this little very simple math, you get an average mass of 12.01. And on the periodic table, carbon has an average mass of 12.01. That's why when you look at all of the masses on the periodic table, none of them come out even. That's because they all exist as collections of isotopes. Any questions? Now, we're actually not going to do this calculation on an exam, but let me just show you one more time how we do this. This is the simple problem. Chlorine. Chlorine is over there in the periodic table. Consists of 2 isotopes, chlorine-35 and chlorine-37. 35 is the most common at about 75%. 37 at about 24, 25%. In order to calculate the mass, you would take the percentages, convert them to fractions, so 75%, 24%, and these are the masses that we measure. Plug these into the equation. So this is fraction times mass, add it all up, and you get 35.45. Again, this is the average atomic mass of chlorine. Whenever we do calculations involving weighing chemicals and stuff, you have to use the average atomic mass because that's always this mixture of these different isotopes. Any questions? Well, you should have a question, or you could. Look at the numbers here, 34.9689. You know, chemists must be pretty darn good to measure something that accurately, and we really are. This is how you do it. This is called a mass spectrophotometer. Very complicated machine. It's all under very high vacuum. You start off with your little sample here. It's ionized, moves into this big magnet, which is here. Because it's ionized, it'll have a charge, and the magnet will bend it. The magnet bends it, comes out at the other end, and you have some array that you can detect it with. Just to show you how accurate these things are, this is for boron 10 and 11. Boron 11 actually weighs 11.009305 at 80.2%. So the accuracy on these things is just phenomenal. They're just amazing little machines. Any questions? All right, let's go back to our friend carbon. As I said just a moment ago, it does have 6 electrons, and they live in 2 regions. These guys in the middle, we call the core electrons. They are closest to the nucleus, and they don't do much. Don't do anything, actually. They just kind of sit there. The ones that are in the outer shell, we refer to as valence electrons. Valence electrons are important to us because these are the guys that make bonds. And remember, chemistry is going to be all about making and breaking chemical bonds. These valence electrons, again, are in the outer shell. They're higher energy. Core electrons, we really don't mess with. All right. Let's go back to our periodic table. Today we will understand why it looks so peculiar. The period here, we said these are periods 1 through 7. These actually represent the levels that the electrons are in. So carbon here is in the 2nd period, so it has 2 levels. The core electrons are in the 1st level, and these are the valence electrons up here. Now, every level can have different numbers of electrons. The formula is actually 2n squared. So this is 2, 8, 18, 32, 50, and on and on and on. Now, within each level, these things live in orbitals. Orbitals are cute. They are really just calculated regions of space where electrons can reside. Every orbital can only hold 2 electrons. Only 2 electrons per orbital. The simplest is called an s orbital, SPDF is what we'll call them, and this is just spherical, so it's a ball. The next one is the p orbital. P orbital is a little more interesting. It actually has 3 lobes oriented x, y, z. So this guy, and this guy. And now each of these can hold 2 electrons. When you look at the p orbital, you really would like to say, oh, 1 electron here, 1 here. Doesn't work that way. It's just a region of space where the electron can be. They both could be here, they both could be anywhere, except they're never in the middle. They get from one side to the other without going through the middle. It's just amazing. All right, so we have 6 electrons we can put in here, 2 each. The d and the f orbitals are the ones that are really fun. I think my favorite is this guy. You know, it's got 2 lobes and then a donut around the middle. These are exotic, calculated regions of space again. Most of the compounds, in fact, all the compounds that we'll deal with in this course are only going to have s and p orbitals. But these are just really fun to look at and think about. All right, let's go back to our periodic table. Our first quantum level. We can put in 2 electrons, and these are going to go in the S. We use 1 to indicate the period, and S to show it's the S orbital, and we can put 2 electrons in it. For our second period, first thing we're going to do is put in 2 electrons, and they're going to go in the 2s. Then we're going to go all the way over here, and we're going to put in 6 more electrons in our 2p's. So this has a total of 8 electrons through here. Our third period is going to look a lot like the second did. Going to put them in the 3s. Then we're going to put them over here in the 3p's. Now, you know, this actually should be able to hold 18 electrons. But the way things are, electrons don't go into 3D until we get down in the 4th period. You don't need to worry about that. But as far as the first 3 periods, all we're doing is putting in S and P electrons. In our 4th period, we fill up the 4s, then we fill up the 3ds, and then over here we'll do the 4p's. But again, we're not going to do the 4th level. Now I said that every orbital can hold 2 electrons, right? These are very special. Something called Hund's law tells us that electrons have a quantum property called spin. Now they're not really spinning, but they kind of look like, or they behave like they are. And when you spin something with a charge, you generate a magnetic field. That means the electrons can be orbited or oriented either up or down in this orbital. Hund's law tells us that if you have 2 electrons in an orbital, one has to be up and one has to be down. There's also one other rule. We're going to put all electrons in orbitals one at a time until, like, the p's are all full with 1 each. Then we put it in opposite spin and fill them all the way up. Hydrogen is in our first period. It has 1 electron. The cutest way to show this is like this. This is our 1s, and we're going to put 1 electron in, and we're going to point it up. Helium is the other element in our first period. So again, we're dealing with the 1s. 1 comes in up, and 1 comes in down. Use this abbreviation, 1s1, 1s2. Makes it easier than drawing little arrows and stuff like that. Now, we are going to write configurations for very simple atoms. So let's go ahead and do one. Carbon. Carbon O is over here. It's in the second period, and it has 6 protons. Okay? We're dealing with 6 electrons. Now, because we're in the second period, the first 2 are going to be our core electrons. They're gone, you don't care about those. The other 4, we're going to put in the 2s and the 2p orbitals. So here's how we do it. The 1s is going to be filled. Those are the core guys. We get down to our second period. We're going to put the first 2 electrons in the 2s. Now we've also got the 2p's, don't we? We're going to put the remaining electrons in these p orbitals one at a time with the same spin. So this will go in like this. Both of them up, 2 electrons in the p. A total of 2 core electrons and 4 valence electrons. This is it all written together, and you will see on an exam simple questions that use this shorthand nomenclature. Again, this is 1s, 2 electrons, 2s, 2 electrons, and our 2p's, we have 2 electrons. Any questions? All right, why don't you see if, without me talking, you could do fluorine. Fluorine, atomic number is 9. So we're dealing with 9 electrons. And again, it's in the second period. Let me see what my son is bothering me about. Our first 2 electrons are going to be in the 1s. Our second 2 electrons are going to be in the 2s. And the remaining 5 electrons will be in the 2p's. Our 1s is filled. The 2s is filled. We have 3 p orbitals and 5 electrons. Now, UN tells us that the first thing you do is put them all in, pointing up. Then you pair them with the opposite spin. Our total configuration looks like this, or 1s2, 2s2, 2p, 5. Any questions? Putting all of this within the context of the periodic table, and like I said, now you can understand why it looks so funny. It's arranged this way because this is just where the electrons go. Up here we're doing 1s, then 2s, 2p, 3s, 3p, and now we're doing d's in the middle here. And when we get down to here, we start sticking in the f's. So that's why the periodic table kind of looks this way. Any questions? Yeah?
Will we ever use the F or no?
Nope, 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 you're not going to use anything past the 3rd period. But we're going to do one right now. Not with F, so nobody wants to get an F. Electron configuration for sulfur. Now this is an actual exam question, okay? Actual exam question. Well, you're right. You need to look at a periodic table, don't you? I happen to have one. So you got to find sulfur. That's always the first step. Sulfur lives right here. All right, so it's in the 3rd period, isn't it? It's also over here in group 6. All right, well, if it's down here, that means that all this other stuff is full. All that other stuff is the core. The core is going to be 1s2. Well, these are all 1s2. Next thing, we're going to put them in the 2s and going to put 2 in. Well, that's all full too. Then we're going to fill up the two P's with 1, 2, 3, 4, 5, 6 electrons. So that's 2p6. Well, they're all 2p6. Gee, so far we're stuck. We have the 3s next. That's going to fill 3s2. So shoot. How many electrons do we have in our P? Very simple, right? 1, 2, 3, 4. Well, that's not so hard, is it? You fill up everything before it, and then you just count over to see where it is. Everyone always misses this question because they can't figure out what I mean by n. N is just the period number, okay? We're dealing here with group 2, okay? What electron configuration do we have in group 2? Well, think about it. We are, in this, we're filling up the S's, aren't we? So this would be 2s, 3s, 4s, 5s, where that's the period, and we have 2 electrons in there. Lithium atom has an atomic number of 3. Lithium is here. Has a mass of 7. We don't care about the mass, do we? Because that's an isotope, right? Number of electrons in the first shell is what? Now, what's the first shell again? What's the other word I've been using for it? Core electrons. How many core electrons does this guy have? Got to fill up this guy with 2 electrons. Number of orbital pairs of electron in this guy. So how many of these electrons are paired up? See if we do these shorthand here. It's easy to write, but you have to understand the pairing thing. Well, that's a pair, isn't it? That's a pair. Now in our P's, we have 4 electrons total. Remember, we put them in 1, 2, 3, and we paired it. Number of s electrons in the highest energy level of scandium-21 is, okay, scandium is here. Number of s electrons? Well, it sounds complicated, doesn't it? But of course it's not. How many s electrons did we put in here? 2. How simple. Now there is a tutorial for this. Because we're not going to focus on this material, I will give you credit for doing it, but to get you 5 points, you only have to do 5. You don't have to do it twice, just once. This is what the tutorial looks like. We've already done sulfur, but we'll just do it again. Determine the electron configuration for sulfur. What you're going to do is put in numbers here. You're either going to put in 1s or 2s. If you put in anything else, you're wrong. It'll mark it wrong. All right, we need to look at the periodic table. You could even push the button and see one. And we're dealing with sulfur. There it is. Now, like we said before, because we're in the 3rd period, we've filled up the first with 2 electrons, right? There it is. We have 2 electrons in these guys. We have 1, 2, 3, 4, 5, 6 over here, but they're 2 at a time. our 3s, we have 2 electrons. And how many in our p's? Well, we have 1, 2, 3, 4. So we have to put these in as a pair and then 2 singles. Go ahead and do this one. This one is so simple, I could do it. We're looking at lithium, which is right there. We're in our second period, right? So that means our first is full. In our second period, we have put in 1 electron, that's it. And that's it. Yeah.
Will we be able to do the shorthand version of it?
Not in the tutorial.
What about on the tutorial?
On the exam, you'll probably, I don't know. Probably. I would say yes, probably. All right. Let's go ahead and leave electrons and electron configuration for just a little bit. And we're going to work our way up to bonding. We're going to start making chemical compounds here. So this is exciting, right? We will see that there are 2 types of chemical compounds we're going to address. They differ in the way that they bond. We will call something like heme. This is the compound that's in blood that carries oxygen. We will say that this is a molecular compound. It's a molecule. And that all the bonds in here are covalent. What covalent means is that the atoms next to each other are sharing electrons. Okay? The other type of compound we're going to deal with, this is sodium chloride, table salt, is ionic. Instead of sharing, the atoms actually exchange electrons. One will give up electrons to the other. We'll have something that's positive then and something that's negative. A pair of ions, and again, this is ionic compounds. Now, in all of this, okay, there, covalent bonds we're sharing, and ionic bonds we're not. All of this is going to happen not with the core electrons, but with the valence electrons. Valence electrons, like I said, these are the guys that you use to make chemical bonds, both ionic and molecular. Okay. To show this process, a gentleman by the name of Lewis came up with a method. Now this was like in the late 1800s, long time ago. Very smart man. But to explain bonding, he said what you want to do is simply look at the valence electrons in an atom. And you can show those valence electrons by taking the chemical symbol and putting them around there. For carbon, here we are. We have 6 protons, we have 6 electrons. In terms of valence electrons, we have 1, 2, 3, 4, right? So we would start off with a C. C for carbon. Now, the rule is we're going to put the valence electrons around there one at a time, singly. When we get more than 4, we So for carbon, we have 4 valence electrons, and they go in like this. And that is the Lewis dot structure for carbon. The symbol and the valence electrons. Now this is so much fun, let's do it again for fluorine. Fluorine, once again, over here, is in our 7th group and in the 2nd period. Go ahead and write it. Start with an F in the middle. You're only interested in the valence electrons. How many does it have? Well, let's count. 1, 2, 3, 4, 5, 6, 7. So we have an F in the middle, and we have 7 electrons around it. The rule is you put them in one at a time, and then you pair them up. Now everybody always asks me, gee, why did I leave the single electron here? Why couldn't I put it here? Well, of course you can. I mean, of course you can. This is simply a bookkeeping tool. And using this very simple tool, we're going to be able to explain the formation of ions and the formation of covalent bonds. Well, I hope you're sitting here asking yourself or saying to yourself, this is really simple, but how in the world do you know how many electrons there are in the valence shell? Well, remember I said groups 1 through 8 were so nice and neat? That's because the group number matches the number of valence electrons. That's why we go 1 to 8. Hydrogen, magnesium, boron, silicon. We're in group 4, 4 valence electrons. It keeps going. Phosphorus, selenium, chlorine, neon. Remember these guys over here in group 8? They were the noble gases, or the inert gases. We call them that because they don't react with anything. That's because they have all the electrons they want. They're full. These guys are all reactive because they want extra electrons. All right. Let's go ahead and do an ion. Let's start with our friend chlorine. Chlorine forms an anion. That's a negatively charged ion, anion, with a -1 charge. We look and we see chlorine is in group 7, right? So how many valence electrons does it have? Well, it will have 7 valence electrons. Now, if we add 1 electron to it, it has an extra electron, therefore it has a negative charge. Not only that, but this is full now, isn't it? As far as electrons go, it looks just like the inert gas argon sitting next to it. So chloride anion has a -1 charge. We start here at chlorine, add our electron, is just like argon, the natural or the inert gas. All right, let's do this again. For sulfide dianion. Step 1, we have to find sulfur. Well, sulfur is right here under oxygen, and it's in group 6. take sulfur and put in 6 valence electrons. You'll note I've paired these up, and we have 2 single electrons. And again, it doesn't matter where you put them, it doesn't matter. All right, to make the dianion, all we have to do is add 2 electrons. We show with a -2, because it has 2 extra electrons. And again, it's full now. Nitride. Nitrogen is here in group 5. Go ahead and draw the Lewis structure for nitrogen. And then make it nitride trianion. Group 5, so we have 5 electrons, 2 of them are going to be paired, and 3 by themselves. To make the trianion, all we have to do is add 3 more. And we have all of the electrons. The p orbitals are all full. Let's do another, one more. Sodium forms a positively charged ion called a cation, C-A-T-I-O-N. Go ahead and draw the sodium cation. Now to do that, you want to start off with the Lewis structure for sodium. Sodium is here. It's in group 1. So sodium has 1 electron. Now, to make it +1, what do? We got to get rid of that electron, don't we? If we get rid of the electron, there are too many protons, and it has a positive charge. Now, once again, I've been pointing out and using a term that these things are filled up. Chemists have a rule for this. It's called the octet rule. You notice that things were full when we had the s electrons and the p's all filled. That's 8 electrons. When you form bonds, these atoms are trying desperately to get 8 electrons. That makes them just like the inert gases. We started with chlorine, made chloride. We went from here to the inert gas argon. We did sulfur, added 2 electrons, gave it an octet. We went from sulfur, again, over to argon. Nitrogen, or sodium. Sodium is here, right? We lost this electron. And when we did that, we moved up 1 period, and here we're at neon. All sodium has left is the core electrons, but those match neon. This is how you form ionic compounds. Any questions? Really kind of simple, isn't it? Well, the other type of compound we said was going to be covalent. Now, if we were to isolate chlorine gas, and we were to analyze it, we would see that it exists as 2 atoms of chlorine. That's Cl2. These are held together by a covalent bond, which means the two chlorines are sharing those electrons. We can show that using the Lewis structure. This is chlorine, it's in group 7, right? All we're going to do is bring in the other chlorine, so they're sitting next to each other. Now if you look, because we can count the shared ones twice, they're really good at sharing, this chlorine has an octet, doesn't it? And so does this one. This is how you make a covalent bond. You share electrons so that things have 8 each. That's the octet. Chemists get really tired of drawing little dots. And we're not going to draw too many dots. Maybe we'll go on the first exam, we'll draw some dots. But in general, when you want to show a covalent bond, you will use the dash. All right, shall we make a real molecule? Let's do ammonia. Ammonia is 1 nitrogen bonded to 3 hydrogens. Okay? Now, first thing you do is find them. We're going to put our nitrogen in the middle, and we're going to put our hydrogens around them. Nitrogen is here in group 5, isn't it? So it will have 5 valence electrons. Go ahead and write that. Nitrogen with 5 little dots, 2 of them will be paired up. Hydrogen is in group 1. It has 1 electron. We have 3 of them. Draw little H's around with their single dot. You should get something like that. Now to make this molecule, all you have to do is scooch everybody up together and let them share. If you look, our nitrogen now has 8 electrons, doesn't it? Now hydrogen only has 2, but remember it's in the first period, it only has the s orbital. That's all you can put them in there. You can only put 2 in. So this looks like helium, if you will, and this looks like neon. If we want to get rid of these, we would change this to this structure. Again, when you see a line, we call that a single bond. And you're supposed to understand that this means we have 2 electrons shared between the nitrogen and the hydrogen. And that's how you make a molecule. Let's do one more. Let's do molecular nitrogen. Nitrogen, again, if we did the analysis, exists as N2. 2 atoms of nitrogen bonded together. Nitrogen lives in group 5, so each one has 5 electrons around it. Somehow we have to arrange these guys so that each nitrogen will have 8 valence electrons. Go ahead and do it. And tell you what, to show you what kind of a sport I am, I'll do it too. Oh, feels good to sit. Here's my 2 nitrogens. Now, clearly, we could form a bond here. That's no problem, right? Everyone sees that. And if we did that, we would have 1, 2, 3, 4, 5, 6 electrons around each nitrogen. That's okay. I suppose, but it's not 8, is it? So what I'm going to do is grab one of these, move it in. I'll grab this guy, move it in like that. Now if we add them up, I have 1, 2, 3, 4, 5, 6, 7 on each nitrogen. I can fix that. By doing that. Now I have 3 sets of shared electrons and 1 set of unshared on each nitrogen. That's what we just drew, right? We have 8 electrons around this nitrogen. We have 8 electrons around this nitrogen. They both have a full octet. Instead of just a single bond between them, however, we have 3 bonds, and we call this a triple bond. Bonds we will see come in single, double, and triple. Double bond, you're sharing 4 electrons. Here we're sharing 6. Any questions? That's kind of neat, isn't it? All right, let's go back to our molecular and ionic compounds. And let's look at a very simple dilemma. We know that in ionic compounds, we are going to transfer electrons. Sodium will give up 1 electron. Chlorine will accept it. We'll have a positive sodium sitting next to a negative chlorine. That's ionic. We also know that we can make covalent bonds by sharing electrons. We have 2 types of compounds, molecular and ionic. How in the world do you know, however, if I just give you a compound, how do you know if it's going to be molecular or ionic? Turns out it's really, really simple. Everyone likes simple, right? Remember our periodic table, we talked about how colorful it is. Remember the regions we talked about. In this particular version, we said that these yellow guys were called nonmetals. They did not conduct electricity. They're typically brittle, etc. The green guys we called semimetals. They were in between the metals here and the nonmetals, and these were our semiconductors. And the blue guys, the blue guys are all metals. All right? The rule, if we have a compound that contains only nonmetals and semimetals, that will be molecular. That will form covalent bonds. If your compound has a metal of any sort in it, it will be ionic. Now, isn't that simple? So let's just do a problem. I have here magnesium chloride. Is this going to be molecular or ionic? Well, what you have to do is simply find them, right? This is why you have to know the basics of the periodic table. Magnesium is sitting over here, and it's blue. It's a metal. Chlorine is over here, it's yellow, it's a nonmetal. If we have a metal in our compound, it is not molecular, it is ionic. hydrogen fluoride. We all know where hydrogen lives. It's this yellow guy in this whole sea of blue. But it's a nonmetal. Fluorine, over here in group 7, it's also a nonmetal. Two nonmetals, a molecular compound with covalent bonds. Silicon tetrachloride. Behind silicon. Silicon's hiding here under carbon. And it's green. That's a semimetal, isn't it? Chlorine, we've already done, is a nonmetal. Semimetal plus nonmetal, molecular. Sodium bromide. Well, that's a simple one. I hope that one's on the exam. Sodium is over here in group 1. Bromine is over here in group 7. This is an ionic compound. Finally, let's just do this one for fun. Remember how I said that nitrogen existed as N2 and chlorine is Cl2, et cetera, et cetera. Sulfur actually exists as S8. 8 sulfurs in a ring. Are the bonds here ionic or covalent? Same principle. Sulfur is over here, it's a nonmetal. So these are all going to be covalent bonds. Looks like a little crown. Any questions? All right, let's go ahead and wind this up with 8 or 10 quick problems. Take this list. I will hush for a moment, and you simply indicate if these are going to be molecular or ionic. This is the degree of difficulty that you could expect on the exam. There is one other difficulty on the exam, however. See how this is nicely colored? See how this is not? Guess which one you get? Yep. So you kind of got to figure out to remember where the borderline is here. All right, nickel chloride. Nickel, we all remember nickel as a metal. Down here in the middle of the transitions, we have a metal and we have a nonmetal. It is an ionic compound or not molecular. Either one works. Dihydrogen monosulfide. Hydrogen is here. Sulfur is here. These are both nonmetals. It is a molecular compound. Silicon tetrahydride. Silicon, we saw, was here under carbon, is green. Hydrogen is here. They are both, well, this is a semimetal and a nonmetal, covalent bonds. Sulfur trioxide. Sulfur is right here. It's yellow. It's a nonmetal. So is oxygen. Molecular compound. Calcium hydride. Calcium lives here. It's a metal. Remember the rule, anytime you have a metal, it is an ionic compound. Let's do one more list. Go ahead and just jot it down. Molecular or ionic, that's all you have to do. CS is cesium. It's down there. And it's a metal. Doesn't matter, oxygen is over here, and of course it's a nonmetal. This is an ionic compound. This guy, diiodine heptaoxide. Something to look forward to. In next chapter, you get to learn how to name things like this. Isn't that neat? Diiodine heptaoxide. Well, iodine is over here. It's a halogen. It's yellow. Of course, oxygen is right there. These are both nonmetals. Covalent bonds. Oxygen difluoride. Nonmetal, nonmetal, molecular. Now I could call this carbon tetrahydride, but that would be, well, that would be such an insult to all of organic chemistry. And I teach organic, you know. Okay. So this is actually methane. Methane is natural gas. Carbon with 4 hydrogens around it. Carbon is a nonmetal, so is hydrogen. These are all covalent bonds. And finally, sodium chloride. My gosh, that's falling off a rock, isn't it? First of all, we have a sodium. We know darn well that that's going to be ionic. We have a metal. We have a nonmetal. This is an ionic compound or not molecular. Either one. Any questions? All right, well, this pretty much wraps up chapter 3. Once again, on Monday, we will do the next lab in the book. Some people seem to be having trouble uploading the lab. Keep trying, okay? Keep trying, okay? Yeah. I have this set so you can do unlimited attempts. You've got this, the thing, you saved it, it's on your computer. All you have to do is just keep hitting the button until it finally works. So, we'll try to do the same thing again. The only tutorial we did today was electron configuration. A lot of you have earned 30 points so far, and I'm so very proud of you. You are certainly proud of yourself too. Remember, before the first exam, that's when the early tutorials shut off. You must have them all done before the first exam. This kind of lets you study for it, okay? While you do it at home and it's fun. Right? Right. Okay, have a good weekend, and I'll see you Monday.
To do the tutorials again, like where do you go?
Where what goes? I'm sorry.
The tutorials.
Oh, okay, sure. Oh.
Take a time.